is calculator. These first couple ones are not calculator. Now, the directions up at the top, it says a couple different ways. You can create a T-chart, or you can sketch the polarity equation in rectangular form and then use the sketch as a table of values. Really, the T-chart is a little bit easier. These first two are very easy. We don't really even need a T-chart, but for the second two, I am going to make a T-chart. Now, kind of like with when we graphed the trig functions, there's a pattern, and if you recognize that pattern, it becomes very easy. You just have to plot a few points. We usually ask for 3 or 4 points that we want to actually see, and then the shape. Because if your shape isn't perfect, it's okay. But if you see that you've plotted the points correctly, and then you weren't very good at tracing and figuring out those out, that's okay. Now, you can't just like connect the dots and make them like all these straight lines. That's not a thing. But again, you don't have to be an artist to do this, but you have to be able to plot points correctly and plot the correct points. All right, so these first ones, you could probably figure out even without me saying anything. So we want to sketch the graph of the equation r equals 3. So we want to go to this polar graph and figure out where r equals 3. Well, here r equals 3. R equals 3 everywhere here, right? All of these points I'm plotting, r equals 3. So what do you think that shape is? A circle at r equals 3. There's the graph. R equals 4, it's going to be a circle at that next ring. 5, 6, 7, 1, wherever it is. 1.7. Hey, could we do 1.7? Of course we could do 1.7. Somewhere right about there. Hey, it would just be right below that second ring. So that's how you graph r equals. The way you graph theta equals is we go to where theta equals pi over 3. So here is 1, theta equals pi over 3. 2, theta equals pi over 3. 3.5, 6.7 pi over 3, 7 pi over 3. Now, we also have the negatives. Negative 1 pi over 3, negative 2 pi over 3, negative 6.5 pi over 3. So notice that forms a line. It goes right through the whole thing. It is not just up here at the positive values pi over 3. Even if you do the slide, 2 pi over 3, slide it down to make it negative. So it's the whole thing. It's a line, and it's got arrows on it. So could you make a T-chart? You could, but it's not really necessary. So r equals the circle at that particular r. Theta equals, it's a line at that particular theta. If that was theta, let's say we made it theta equals negative pi over 3. Okay, so here we go out to 2, negative pi over 3, ends up right there. 4, negative pi over 3. Or we go to negative 1, negative pi over 3. Negative 2, negative pi over 3. So there would be the line theta equals negative pi over 3. It would match up to theta equals 2 pi over 3. Those would be the same. So there are things that repeat. Hey, you just have to go to that particular place and draw that graph. Now, these next ones, they're not difficult, but they're not quite as straightforward as those are. So r equals 2 sine theta. We have no idea what r equals 2 sine theta looks like. So this is where you want to make a T-chart. With our T-chart, we want to, and now I will tell you because it's sine, things are going to reflect across the y-axis. So in this one, because there's nothing plus or minus, like if we look at this one, 2 plus 2 cosine. Now this could be 2 plus 2 sine. The sine and cosine have nothing to do with these shapes. Okay, the form has to do with these shapes. So we're going to have these two shapes that we do without a calculator. We're going to have a shape formed like this with no plus or minus, and then a shape formed here with a plus or minus. Now, everything we do, these numbers are going to be the same as far as the non-calculator goes, because there's some rules you have to learn about it, but we're not going to go that far into it, so those numbers would always be the same. All right, so let's think about, now it's a little backwards because there's our theta that we're going to pick, and we've got to figure out what our r is. Now, don't write all these down yet. Okay, I'm going to write everything down from 0 to pi. So we have the ones that we know. We have 0, we have pi over 6, pi over 4, because we aren't going to do all these because we don't really know exactly what all of them are without a calculator. All right, so now we want to pick the ones that we know. So how do we know what we know? Well, let's think about this. Going back to our unit circle, we're dealing with sine. We're finding sine of some angle. So is sine of 0 easy to find and plot? Yes. We can plot a 0. Can we plot a half? Yes. What about root 2 over 2? Do we know what that equals right off the top of our head? Probably not. Root 3 over 2, not so much. I mean, we could estimate and figure it out. But we want to pick the ones that we know. The reason for that, now, that's not going to necessarily give you the shape. I'm going to give you a little bit more information. But once you know that shape, then you just know, okay, this type of equation makes this shape, and it just makes it much easier to do. So when we do 2 times sine of 0, we get 0, which is 0. So we plot that point, 0, 0. Pi over 6 we like. Sine of pi over 6 is 1/2. So 2 times 1/2 is 1. So at pi over 6, r is 1. So we go to r is 1, pi over 6. We didn't like pi over 4, we didn't like pi over 3, but we liked pi over 2. So 2 times sine of pi over 2 is 1. So 2 pi over 2. And then we didn't like 2 pi over 3 or 3 pi over 4, but 5 pi over 6 we like. 2 times sine of 5 pi over 6, 1 equals 2. So 2, no, I did something wrong. 1/2, thank you. Sine, though, it's positive, so we get 1. So we're at 1, 5 pi over 6. Now look at these points. See how they reflected across? So whenever we have sine, points are going to reflect across the y-axis. Now we don't have any other points, so right there, because this is 0, we already found that, we don't have to worry about going on. Because if we did 7 pi over 6, we could, or let's do pi first, sorry. So 2 times sine of pi is 0, which is 0. So notice we're back to where we started. If we get back to where we start, then we don't have to keep going because things are going to repeat. If I did choose 7 pi over 6, I get 2. Now I get negative 1/2, right? So negative 1, 7 pi over 6, or 1, 7 pi over 6, and slide it, we get back to that same point. So it just keeps repeating. Now, again, from those points, we don't really know what that looks like. Now, if we had done pi over 4 and pi over 3, pi over 4 is about 1.4, and this is about 1.7. Again, not something that you have to know without a calculator. I'm just going to plot those so you can see what happens to this shape. So at 1.4, we were at pi over 4, and at 1.7, we were at pi over 3. So now you can kind of see that shape looks like it's going to be a circle. And then those reflect over to the other side. Not a very good circle. Again, doesn't have to be perfect, but if you have those points plotted, then it's okay if it's not perfect. We would expect 3 or 4 points. It'll always tell you 3 or 4, I don't know which one it is, one of those two. And there's your graph. Now, what do you think would happen if I made this negative 2 sine theta? Yeah, so it'd be down here. What about if I made this 2 cosine theta? So if sine's on the y-axis, what do you think cosine is? On the x-axis. So it would be a circle over there. And negative cosine would be a circle over here. So you just remember that that form is sine or cosine. And also look at this 2. This 2 matters. So 2 sine or cosine, notice the diameter of that is 2. That's going to happen. If that was 4, this would have been up at 4, or over at 4, or down at 4. So those things do happen. If you recognize those things, fine. You don't have to. You can make a T-chart. But if you're good at memorizing, you just know, okay, that's a circle, and I know my few points, you can plot those points and draw that circle. Okay? So again, the sine or cosine doesn't deal with the shape. Sine or cosine deals with the x and the y-axis. Does that shape move along the x axis or the y-axis? Okay, so that's the circle, another circle that is formed when the equation looks like this. The other one without a calculator is in this form. And this is kind of like r equals a plus b cosine theta. You know, if you have your m and b, like if your slope-intercept form of a line, m does something, b does something. Okay, the a and the b are kind of the general form. So when you see it in that form, just r equals a plus b, so a number plus a number times cosine or sine, then we're going to have this other shape that we're going to form here. All right, so same thing. We're going to have our theta and our r, but now we're going to pick different ones. We're only going to pick the ones that we like for cosine. If that was sine, we'd pick those same numbers that we like for sine. We always like 0. Okay, we always want to start with 0. So 2 plus 2 times 1, cosine of 0 is 1. So we get 4. So 0, 4. Then we don't like pi over 6 because that's root 3 over 2. Pi over 4 we don't like, but pi over 3 is a good one. 2 plus 2 times cosine of pi over 3 is 1/2. So 2 plus 1 is 3. So when r equals 3, we're at pi over 3. Yes, ma'am? We just at our unit circle. So now we're with cosine. So do we know that number without a calculator? Do we know this number? Can we plot a half? Or can we use a half? Can we multiply a half by something really easily? Yes. I mean, we can do all those and estimate them, but we don't need to get our shape. Okay? Pi over 2 is something we can deal with real easily. It's a nice rational number. 2 plus 2 times 0, we get 2. So at 2, we're at pi over 2. So notice this one looks a little bit different than the last one did. The last one just kind of curved. It still curves, but now it's curving back down. But we've got to keep going. Okay, we've got to find all of them to pi. So we like 2 pi over 3. Again, we like 2 pi over 3 because we know cosine of 2 pi over 3 is a rational number. So 2. Now 2 pi over 3, we're dealing with cosine, so that's negative 1/2. So 2 minus 1, we get 1. So 1, 2 pi over 3. And then 3 pi over 4 and 5 pi over 6, those gave us irrational numbers, so I'm not going to pick those. So I'm going to go ahead and pick pi. 2 plus 2 times negative 1 gives me 0. So 0 pi, I'm right here. So what this forms, if I kind of curve and connect those dots, have like half a heart. But now I could keep going, and we said earlier, sine is always going to reflect its points over the y-axis, so therefore cosine is going to reflect its points over the x-axis. So that means this 3 pi over 3 reflects down here. This 2 pi over 2 reflects down. This 1, 2 pi over 3 reflects down. And we have the other part of that. So circles and hearts. The circles are if there's no plus or minus. The heart if it's in the form something plus something. So a number plus a number. And anything we do without the calculator, those numbers are going to be the same. They're both going to be 2s, 3s, 4s, whatever it is. Because when it's different, it changes it up a little bit. But that's what we will have. So lines and circles on the actual axis, or if you have a sine or cosine with a multiplier out in front of it, a scalar, then it's going to be a circle that either is on the x or y axis or a heart that's on the x or y axis. So, like the last one, if I were to make this 2 plus 2 sine theta, this would just move up here, and it would be kind of a heart that looked like that if we made it sine. The what? The numbers, like the a plus b, the two numbers being added. And they're the same. When they're not the same, other crazy things start to happen, but we're not going to go that far into it. All right, so those are the 4 graphs without the calculator. Now with the calculator. All right, so a few things. Now, on your quiz Friday, there is going to be no calculator, but your test, there will be. Okay, but Friday, so we still have to do this because this is going to be on your test this unit, but Friday will be all non-calculator for your polar quiz. So the first thing to do is to change your mode to polar. Hopefully it's in radian. If it's not in radian, go ahead and put it in radian. And the mode is just that mode button, and then you go down, I think, 4, right there, function. That's parametric, which we will do in this unit also in polar. So you just scroll down and hit enter on polar. Again, make sure you're in radian mode as well. The other things on this, okay, adjust your window to the appropriate domain. The problem is going to tell you what the appropriate domain is. So you will know the problem will say graph this on this domain, just like it says on your notes. The x min max, x min and max, y min and max is still the same as it was with y equals. Okay, it's going to tell you how far up and down the graph goes. And then we might have to straighten the screen out a little bit when we get there. Zoom in or zoom 5, but it just depends on the problem. So when we get there, we will do that if we need to. All right, so this first one, graph the equation r equals 4 sine theta. Okay, well, how do I get an r? Well, now that we're in polar mode, you hit y equals, and it automatically does that for you. Okay, on this screen right here, you have x when you're in function. It changes to t when you're in parametric. It changes to theta when you're in polar. Okay, so that x button is still what we use, but when we hit x, it's going to be a theta, just because we're in that particular mode in the calculator. All right, so before we do anything, let's just plug it in. So we have 4 sine 4x, which again automatically comes up as a theta. And let's just graph it and see what happens. Well, actually, we need to do it on that domain. So let's go to our window. Now, it defaults to 0 to 2 pi. So if you forget about that, it's not a big deal. But sometimes it does more, like that second one is 0 to 6 pi. That's going to be a big deal. So 0 to 2 pi, 6.28, that's already 2 pi. If we didn't recognize that and we just went ahead and hit 2 pi, and then once we scroll down, it changes it to that number. Okay. Oh, so my screen is in some crazy mode. So I'm going to zoom 6 just to get it back to normal. And that's what graph you should get on your calculator. Now, it says if your graph looks kind of funny, you can zoom 5, makes your screen an actual square. Okay? So zoom 5 just kind of straightens everything out a little bit to where it's not quite so distorted. If you don't want to see that much of it, we're at 15, maybe make that, I don't know, -6, whoops. And make that, we'll just change that -6 and 6 and just see what happens. I don't know, because we just didn't want to see that much of it. Kind of lets you see a little bit closer. Zoom in might work. I don't know, I don't like zoom in, but sometimes it works, sometimes it doesn't, depending on the problem. Okay? Now, how do we graph that? We could draw a sketch of it, but we need some actual parts to it. Okay, so you have to know a little bit about this problem. The calculator doesn't do everything for you, because how do we know exactly where all of those points are? Okay, so first of all, this right here. So these little things are called petals or leaves. We're going to call them leaves. Okay, so this tells us the length of each leaf. Again, some people call them petals, leaves. That number right there. So we know from the middle out to the end point, each of those is a length of 4. What this number in here tells us is it's important if it's even or odd. Okay, it's an even number. Now, it's going to tell us how many petals there are. But, I mean, do we need to know that? We can all look at this and see that there are 8 petals or 8 leaves. 1, 2, 3, 4, 5, 6, 7, 8. So what you do, if this was like a non-calculator problem, okay, this will tell you the number of leaves. If even, multiply by 2. If odd, it stays the same. So if that was a 3, if I went back to y equals, and let's just say, don't do this, but if I change that to a 3, that means when I graph it, there's going to be 3. But if it's even, you multiply it by 2. Okay, so that's just kind of some helpful information, kind of make sure you graphed it right. Now, the next thing, so we know we go out 4, but we don't know where we go. Okay, so we have to do a little bit of very simple math. We've just got to figure out the midpoint of different things. We know that there are 2 per quadrant. We also know there are 8, and they're always the same distance apart. So if there are 360 degrees and we divide that by 8, that means each of those is 45 degrees apart. Now, if one of those leaves was on the x-axis, that'd be really easy to plot that. Still not difficult, okay? But we know that we have 2 per 90 degrees. So in this 90 degrees, if we cut that in half, and then we find the midpoint of the middle, then we have our point. So halfway in between here, so those are 3 equal sections. So halfway in between 3 equal sections is 1.5. So we go out 1, 2, 3, 4 rings, and we plot that point. And then halfway in between here is right there. And then we just keep doing that all the way around. Here's halfway in between there, right here. Halfway, right there. Halfway, halfway. And you can see that you are the same distance apart. All of those are the exact same distance apart. Now, sometimes, again, it lies on nice angle that's already there, but sometimes it doesn't. So you just got to kind of do a little bit of simple math to figure that out. Now, from this point, it's just a sketch. We know those dots that I drew are all the endpoints. Now, again, we usually ask for 3 or 4, but in this one, you'd want to plot all 8 so that you graph it correctly. So we just kind of, now you could be more exact. You could plug in a bunch of numbers, but again, you don't have to at this point. You've plotted more than enough points, and there you have your graph. If, again, going back to when I changed that to a 3, if I change that to a 3 and I graphed it, now how far apart are those leaves if there's only 3 of them? 120, right? Degrees, we can think of that in degrees. So we know this one, this length is still 4. So we're still 4, but then we just need to go 120 degrees. We know from here to here's 120 and here to here's 120. So 90, 120, there's a point, 90 and 120. That one was way easy. We had way less math to do on that one, okay? So it just depends on the problem. You just have to figure out how far apart they are, because there's no way to look at this graph and figure out what that point is without having to do a little bit of something that the calculator won't help you with. Because the table doesn't really help you with that, because you don't know, I mean, even though you know this is 4, that doesn't help us with much, okay? All right, now this last